Sure, yeah. Hi, everyone. Thanks for having us at the Graal Workshop this year. My name is Maple and Chris from Shopify. Chris, would you like to introduce yourself?
Yeah, I'm a senior staff engineer at Shopify. I've been working on Truffle, Ruby, and Graal stuff since 2013. I work from home in Cheshire in the UK.
Cool. I'm Maple. I'm a senior developer from Shopify as well. We both work on the Truffle Ruby team on the Ruby and Rails infrastructure team at Shopify. So if you didn't know, Shopify is a Canadian e-commerce company. We let people run their own stores, both online and in person. It's likely you've probably used a store built on Shopify before. Our product is built on the Ruby programming language, and our team is working on ways to make Ruby significantly faster in the long term using compiler research. So today we'll be presenting the call target agnostic implementation of method arguments. We'll be using Ruby, the Ruby programming language, as an example, but the proposed implementation may be applicable to other dynamic languages that have variable-sized method arguments list. So just to start off, a brief introduction to the types of method arguments in Ruby. Ruby is a dynamic language that allows for positional arguments, keyword arguments, or a combination of both. Just to add some context, Ruby is the primary programming language at Shopify, and we want to ensure that our developers are having a good experience with the language. So our goal as Ruby implementers is for Rubyists to use keyword arguments when they think it makes sense and without worrying about the cost and performance. And we don't want people deselecting keyword arguments just because of the performance. So in this code example, we're just showing that the positional arguments can be called without the keywords, and keyword arguments are called with the keywords. And on the right, you can see like it's a combination of both. So on top of these static keyword arguments, Ruby also supports sending dynamic keyword arguments through splatting, which you can see is denoted by the double asterisk. So you can splat an existing Ruby hash. And just for also additional context, a hash in Ruby is like a dictionary or a map, which is like a collection of key value pairs. And it treats it as keyword arguments for a call. So we won't be covering that case here, and it can be left implemented as usual. So let's quickly go into how argument handling works between call site and the call target generally. So first, arguments are converted to the generic representation compatible with all call targets. In Ruby, the arguments are placed in a Ruby hash object that is heap allocated. Next, the arguments are pushed onto the stack and then the receiver is looked up. Then the arguments are dispatched to the call target, where the arguments is then looked up within the Ruby hash. Because the arguments are converted into the Ruby hash at the call site, this style of argument handling is known as the Callsitespecific implementation. So this code example demonstrates how it works. You can see that the Ruby hash is allocated at the foo method call site, and then immediately consumed at a call target where the foo method is defined and then never to be used again. The compilation boundary is between the allocation of the Ruby hash and the use for non-inline cases. And this kind of defeats any compiler optimization that Graal provides. So let's talk about call target specific implementation. In the paper called Call Target Specific Method Arguments by Nipals et al., a new way of argument handling is proposed. So how does it work? The arguments are converted to the call target specific representation before the method call is invoked, making the argument handling part of the polymorphic inline cache entry. This implementation puts the responsibility on the call site to manage the arguments, and that is possible in Truffle due to the inline caching mechanism that we have, which means that we normally know what the call target is for a given call site, even though it's a dynamic language. So you see the two methods here, foo and bar, with A, B keywords. The work is done on the call site in that if condition to figure out the order of the expected keywords of the call target before it is invoked with the arguments. So this is a figure extracted from the paper we mentioned. Taking a look at the figure on the right, we can see that there are different variations of arguments created per call target. So the standard implementation of Ruby, what we call CRuby, uses this implementation to a degree. It requires some logic on the call site to shuffle arguments into place and then loop on the call target side to find the correct arguments. And ideally, we don't want any control flow to read arguments, so this is not exactly ideal for us. So what is our hypothesis? So Ruby can be polymorphic, so call target is not always static at the call site. So in this example, you can see that class foo could be doing multiple things depending on which class A or B was created. So by making calls call target specific, we're adding more work at the call site. So while the call target specific implementation would make it easier for the call target to receive arguments because it's already arrived, it will have already arrived prearranged. Implementing it in practice can be complex because there are multiple mixes of arguments, both from the call target and the call site to handle, such as the method's default values in Ruby. The call target specific implementation puts the cost of the extra complexity on the call site. The idea is fundamentally that all call sites put keyword arguments into a common expected format by the call target. And because Ruby is polymorphic, this solution to argument handling isn't ideal because there may be more call targets and call sites. It doesn't help that Ruby's meta programming is also kind of like a more extreme version of polymorphism, can make the call target completely unpredictable. So other considerations. These existing implementations are, as we've shared, not optimal for Ruby. The Ruby hash created as a generic representation of arguments may fail escape analysis, or worse, in non-inline cases, the Ruby hash will always escape. Even in inline cases, escape analysis will fail with a large amount of keyword arguments, which go over the object size budget. The non-inline performance use of keyword arguments has an overhead in both CRuby and Truffle Ruby. And the shame of it is that it kind of discourages developers from using them. Another note is that when we optimize code, we optimize up to the method boundaries. However, keyword arguments straddle a method boundary, which goes against how we would usually optimize a compilation unit. That said, this problem requires a bit more creativity to solve. So what is our big idea that we want to share today? As I previously mentioned, our hypothesis is that there's going to be more call sites than call targets in a realistic application. So it makes sense to shift the complexity from the many call sites to the fewer call targets. Our idea, therefore, is for call sites to send arguments in any format, and for the call target to dynamically adapt to the arguments that it receives. Because the package arguments can be unpacked by any call target, we've called this implementation the call target agnostic implementation. So let me quickly and briefly describe to you how this implementation works, and then Chris will go into the detail. At the call site, the argument values are translated into a flattened representation, and then we pair it with a static descriptor that stores the keywords. The data is then pushed onto the stack and the receiver is looked up and then dispatched to the call target. The call target intelligently uses a flattened array and the static descriptor to unpack the arguments according to the index of each argument. So exactly how does that work?
Yeah, so I'll talk about how the idea works in a little bit of an abstract and then go down into how it works practically in the implementation. So this is a standard positional call with two positional arguments where the arguments are added together. These are called by passing A and B simply as flat arguments, as you'd expect in any other language. This is how that looks when we modify it to use keyword arguments. So now the arguments are named and we call them using those names. This is logically how keyword arguments are implemented. A Ruby hash object of the keywords and values is constructed at the call site and sent as an extra argument to the call target. Call target then does a normal full hash lookup, and that may involve loops and other complex logic to look up the values in the hash. You can understand how that's slow, how it involves an allocation, how it involves lots of control flow. So this is where we start to talk about our idea. Instead of sending the Ruby hash of the keyword arguments and the values, we instead send a separate list of the keyword names and a list of the keyword argument values. The keywords passed, their order, and the values could vary every time the call is made. So to get a particular keyword argument value, logically, we search the list of keywords for the keyword we're looking for a particular value, and then we index that same value out of the arguments array to get the value out. You can also reconstruct a full keyword argument hash if you want to do by adding all the names and values to a new Ruby hash object. That will give us the same performance as before, the same behavior as before, without requiring any coordination between the call site and call target. The call site simply sends this bag of keyword names and this bag of the keyword values, and the call target goes through the bag each time and finds out what it needs. This is the key optimization. We observe that each individual call site is likely to send the same keyword names each time, and that the call target is likely receiving a small number of different keyword name lists and different orders, even from different call sites. Since the keyword names are likely the same at each call site, the keyword name list can be stored as an immutable value at the call site. Since the number of keyword name lists received at the given call target is likely low, it's possible to inline cache with a pointer comparison against the expected keyword name lists. With an inline cache on the keyword name list, we can turn the indices of the keywords in the value list into constants. This turns the keyword argument lookup into the same logic as a normal positional argument, reading based on a constant index. The only additional overhead we have compared to the position argument is that one machine word comparison guard in the inline cache for the expected keyword name list. So now the keyword values are being read just like positional arguments. So at location 0 and location 1. The only thing we're adding over positional arguments is we check that the keyword list is the same as what we expect. And this is an immutable value and is unique across the process. So we can simply do a pointer comparison. So exactly the same as positional arguments now. The only difference is that guard, and the call site is also very simple. We simply send that immutable value of keyword names and then the keyword values, which we can pass flat, so we don't have to allocate a separate array to do that. Like with the method call inline cache, the cache on keyword names degrades gracefully, handling n for some given value of n, different keyword name lists at a given call target, or beyond n, reverting to a full lookup in the keyword name list. And that's not any worse than currently. So the degraded case is what we currently have, and the hot path is better than that. So if there's a meta program in send, which dynamically generates new keyword argument names every time for some reason, a new list of names will be generated each time, and the call target would transition to doing a full lookup, which would be no worse than before. In the case of a normal call with no keyword arguments, we're conceptually checking that the keyword argument descriptor is empty every time. So have we added this overhead for positional arguments? And that would be unacceptable because we want users to only pay for the overhead of keyword arguments when they're using keyword arguments. However, we can use a feature of Truffle here called call site argument type profiling. We won't go into huge depth on it, but we make the empty argument descriptor a different class to the non-empty descriptor. Truffle profiles the type of arguments going into call targets, and if argument is always the same class, so always empty, then Truffle will inject that profile into the call target, and it'll be compiled with the assumption that it'll always be empty. And therefore, this check here becomes a constant value true and goes away, and we have the same code as we had before. Let's look at how the idea works in practice. I'm afraid I'm going to show you some Truffle code. I know it's not a Truffle specific workshop, and it can be a little in depth to look at the DSL, but bear with me. Work on top of Graal, the Truffle language implementation framework makes it easy to implement this design. There's almost no modification needed to the call site. Instead of constructing a Ruby hash, it passes the values as flat extra positional arguments, and it passes that constant list of argument names. Now, the call target has a polymorphic inline cache, as on the screen, on the argument names list object identity. So each inline cache entry has the logic to unload each keyword argument values into their local variables based on the constant index for that given list of names. So this is implemented in Truffle using the specialization mechanism of the Truffle DSL. Won't go into massive depth, but we have two specializations for an empty list of keyword argument names, in which case there's nothing to do. And we have a cache for a given descriptor. So we have that should be non-empty keyword descriptor. And we have the non-empty descriptor that we've cached that we've seen before. And we simply compare that they're the same. That's that machine word comparison. And then we have a loop going through the cached descriptor. And for each keyword we receive, we unload it into its local variables. And because if we have an explode loop, Truffle turns that into linear code. So we have that one check, and then we have simply unloading the arguments into their local variables. This separation of dynamic data, so the keyword argument values, and the static data, so the keyword names being sent, is a pattern we see in many areas of dynamic language implementation. It's similar conceptually to object shapes or hidden classes, where an object contains dynamic data, but is described by a static descriptor. And this allows the VM to specialize for the static descriptor, even while the data is still dynamic. So this is effectively argument shapes.
Right. So in the same way, our implementation splits the keyword arguments into the static descriptor and the dynamic data, which are the values. So both static descriptor and dynamic data are passed to the call target to unpack accordingly at runtime. The static descriptor is unique, canonical instance in the VM, so we can compare by address in the machine code. The dynamic data is just a flat array, so it can be passed as a range within the existing arguments array, so no additional object needs to be allocated.
As I've alluded to before, optimizing method arguments is an interesting design space because of fundamentally they straddle a compilation unit, unless where the call site is inlined, and we can't inline all call sites. We can't rely on that. So normal optimizations where Graal is extremely effective don't apply to method arguments. For example, we said that previous keyword arguments are logically a Ruby hash, a dictionary object. So why can't we rely on Graal's exceptional escape analysis and scalar replacement of aggregates to remove the Ruby hash and optimize the keyword arguments to flat representation automatically? Well, since the Ruby hash by definition logically straggles that method boundary, which is often going to be a compilation boundary, that optimization doesn't apply. Hence the need for more creative solutions optimizing these kind of things.
That said, the implementation we've developed still plays to Graal's strengths. The way that the call target specializes based on the descriptor relies on Graal and Truffle's powerful ability to create efficient inline caches on arbitrary guards. Also, dynamic de-optimization means that the specialized code is compact, and the fallback case, in the case where there is an unknown descriptor, can be handled entirely by the interpreter. We've done a proof of concept for the call target agnostic implementation of method arguments, and it is currently in the process of being merged into Truffle Ruby.
Let's look at what this achieves practically when it's implemented. We think we can best look at the impact of this optimization by looking at the compiler graph. So this is a Graal IR compiler graph. It's been extracted from Truffle Ruby, and then it's been rendered using Seaton, which is a Shopify tool. So if you're not familiar with the graph, the thicker red arrows represent control flow, the thinner green arrows represent data flow, and the boxes represent data sources or operations of some kind. So this receives A and B as two positional arguments. The positional arguments come in here in the ovals. They get added together by this combination of nodes, and they get returned, and the control flow starts and then runs through to the end. So this is pretty good, right? This is excellent code for something that comes from a high-level language and has been optimized well and produced something fairly optimal. The compiler graphs for the old implementation of a method using keyword arguments, so an add routine with A and B turned to keyword arguments, is much more complicated. And we can see, even without zooming in and looking at specifics, this is a very large graph with a lot of complexity compared to positional arguments, has many branches and many guards. And actually, this graph is already pretty good because of Graal's optimizations for example, small hashes in Truffle Ruby. I mean, there's no loops, which is great. It's unrolled, but it's still so much larger than the positional arguments. This isn't what we want. So this is the compiler graph using keyword arguments using Calltarget agnostic implementation. We can see instantly how much simpler the graph is. There's no branches, there's no loops. It's very similar to the first graph for positional arguments. If we zoom in, this is the the one thing that's changed is this guard node and the inputs to it. And that guard node is the only extra cost for using keyword arguments. It's the test that the keywords passed were as expected, that the keyword value, and then the keyword values can be read out of the arguments list as if they were positional. So we guard that the arguments descriptor is the same as a constant expected keyword descriptor. Then everything else runs exactly the same as position arguments. Now that extra guard translates into a compare and a jump not equal pair of machine instructions. That's the only overhead for using it. The great thing about using these graphs is we can test in CI that the optimization is applied correctly, because it doesn't, we don't need to benchmark, we don't need a benchmark instance to do it. We can assert that keyword arguments are implemented without control flow in CI on a commodity CI over provisioned instance. We wanted to emphasize in this talk specifically the impact on compilation time and generated code, because so often additional truffle optimizations add extra complexity to the interpreter, right? We add extra cost to the interpreter, make the interpreter more complicated, make the interpreter slower in order to make code faster when it's compiled, which, as per Stefan's talking about, can be a bit of a problem for truffle languages, creating bloat and bad startup times. Our optimization simplifies the overall logic in both the interpreter and the compiler, because there's no hash access routines. So in this table, we've shown the impact of that, not on peak performance, but on compilation time and the compilation process. So we have benchmarks for a lot of keyword arguments, so long, and a small number of keyword arguments, short. The caller and the callee. We looked at the existing implementation using a full hash and call target agnostic. We looked at the compilation time and how that reduced. We looked at the size of the AST, how that reduced in many cases. We get an extra guard in one case. We looked at the size of the Graal IR, which is generated, and how much that reduces. We looked at the code size and how much that reduces. In some cases, that an order of magnitude simpler for the case we're talking about here. We're still working on peak performance numbers while we finalize the implementation and get it merged, but the benchmarks are encouraging. So to wrap up, Ruby keyword arguments are logically very expensive. The model that programmers are taught about how they work is expensive. You pass a Ruby hash object of keywords and values, and you have to look up the values you want them. It's simple and it's elegant, but it's expensive. Previous published work tackled at the call site by putting the arguments into a standard order for the call target. But this requires definitely knowing the call target, and it requires extra work at the call site. Our hypothesis is there are many more call sites than call targets, so that's the wrong place to put the cost. So it makes more sense to put the work at the call target. Ruby's idiomatic use often means you may not know the call target. Therefore, instead, we have the call site send a description of the keyword arguments and separately their values, and have the call target inline cache against the description. By looking at the compiler graphs, we can see a massive reduction in complexity using our approach, both on the call site and the call target. We can see this reduces the impact of compilation time, the size of the graphs, the time to compile, the size of the generating machine code. We can also see this reduction in runtime when we benchmark. We're still working on our implementation, and benchmarking is tricky because Graal in some cases is inlining and things like that. So we're not sure quite the right way to test it yet. And this is a rare example of optimization which reduces complexity rather than adds additional complexity. We'll finish up by saying something about academic and industry collaboration. Shopify is increasingly setting up external research collaborations with very high-level researchers. We have major collaborations with Steve Blackburn at ANU, Stefan Marr at Kent, and Laurie Tratt is now the Royal Academy Shopify Research Chair of Language Engineering. We're interested in more of these collaborations, working on dynamic languages, so please talk with us if you're interested in doing that. Thank you very much.
Thank you.
Thank you, Maple and Chris. That was awesome presentation. I liked your format of going back and forth. It was definitely more interactive than a single person presentation. I did not have any questions. I'm asking others if they have any from the audience.
I can't see the chat, so you'll have to read out if there are any.
Yeah, I don't see any. Oh. So I wasn't paying close attention to the beginning of the talk, but how much of your environment involves Ruby? How important is this?
So the Shopify monolith is written entirely in Ruby. Shopify is keen on Ruby. It's not a legacy language for us. We still think it's the best language to use going forward. So we have a very large code base. I do have public numbers. I can't remember off the top of my head. And a very large number of engineers working on it. We have a few satellite services. They're also written in Ruby. We only use other languages for a very small number of very specific cases. So Shopify is keen on Ruby. We have a lot of Ruby code. We're very enthusiastic about the future of Ruby and making it as good as possible for our engineers. What we want to do, I think, is to do language engineering to empower working programmers. So we don't want our working programmers worrying, are keyword arguments expensive? Do I need to worry about that? We want to enable them to just use the language features they think make sense to them without having to follow them around and say, oh, that's a slow pattern, that's a slow pattern. We'd like to transparently remove these hidden costs for them so they can use what they want.
Okay, thank you. I think Stefan has his hand raised. Stefan, go ahead.
Yeah, thank you. So one bit of work that came up, I think 1 or 2 years ago, was a contextual dispatch paper the R people and Prague did. And I think they kind of use a similar approach. So I was wondering whether there are other kind of language features in Ruby that you would think that could benefit from that kind of passing in a shape, kind of a static descriptor into the call.
Yeah, I mean, this is something that I'm increasingly seeing as we try to optimize more complex features of dynamic languages, that split between a static description and a dynamic component is really powerful. Hidden classes is the key example. We can do the same for frames. We can do the same for arguments, and it's the same pattern again and again. And yeah, I think there are some more creative aspects there. For example, strings passed into an eval. If a string is dynamically generated, if we have a rope representation of strings, such as Truffle string does, can we statically recognize the shape of the string, which doesn't change, and separately recognize the data inside it, which is changing, and therefore treat what appears to be a dynamic string as something separately? I think that's a crazy example, but I think there's many examples like that where this kind of separation of static and dynamic is the way to think about optimizing dynamic languages.
Okay, cool. Thanks.
Thank you. I don't see any more raised hands or questions, so let's thank the speakers. Thank you again, Chris and Maple.
Thanks.
Awesome.
Thank you.